My name is Gosia Konwerska. I work as a kernel developer here at Wolfram Research, and I'm going to give the traditional talk on time series processing. Time series is not a new object in Wolfram languages. It's been around for a while, and my talk is in no way, I would be not able, even if I rush super fast, to cover everything. So this is a subjective selection on the topics with focus on the new functionality. So the plan is a short introduction, and as you see, I start with 0 on my enumeration to kind of keep in mind that when we talk about serial data in Mathematica, automatically we start enumerating at 0. So I will talk about the new functionality of direct arithmetic and function application, and about a bit of processing functions for time series. Then our redesigned moving map, so the changes and the augmentations to the moving map, and then about the proliferation of time series that we see throughout Wolfram language. So we have 3 types of serial data in Wolfram language. These are the time series, which is probably the most known, event series, and temporal data. And temporal data is existing in Mathematica since version 9. So that's the oldest object. So time series. The basic assumption about time series is the observations that what we have are in the continuous time, and there is only one path allowed to be stored in the time series, and it could be univariate or the multivariate, but the dimension must be consistent. By default, the values between the timestamps are being interpolated. This method of interpolation, how we want to fill them in, can be set, and by default this is in linear interpolation. So a few examples that I have here are just playing on the precision in a way. So I can define the simple time series with random real, so that's the values, and then the time starts at 0. So this is the way to extract the path for people who is completely new to time series. And then the question of interpolation between the timestamps is, what do you get if you ask TS real of 1/2, right? So our timestamps are integers here, 0, 1, 2, and so on. And what do we get when we ask for the value in between the given timestamps? And in this case, this is the linear interpolation, so we get the real value. Another example, I'm going to have the integer values and integer timestamps, so you can see how the path looks like. And in this case, when we ask for the value in between the timestamps, we get an integer because of the nature of the time series. But we can also have the integer values and the real timestamps. And then if we ask for the value in between the timestamps, we're going to get machine precision because our timestamps were in the machine precision. And if those are taken into the calculation of the value in between the timestamps, then this precision is going to carry over. I mentioned that the method of interpolation between the timestamps can be set, and this can be done if we can kind of redefine the time series, so define time series on the existing time series and set the resampling method. And so this is what I'm doing in defining TS3. So I take the previous time series and I'm redefining with the resampling method of interpolation, where the interpolation order is 0. So now when you look at the paths, they are absolutely the same, because I didn't do anything to the values that are the observations. I only changed the behavior in between the observations. And in this way, when you look at what we get at the 1/2 is the value being held from the left, so it's 10. The other way to change this behavior in between the timestamps is to, for example, set a constant. And I have here actually a symbol, A, and you can see that I changed the TS real with this resampling method, and the path didn't change, but of course when we ask what is the value in between the timestamps, it's going to be a symbol. And also I would like to point out, when you look at the small outputs here, they have small plots in each output. And the small plots are going to kind of refer to what we can get when we plot this time series. So in this case, we see that there is a linear interpolation here In this case, I changed the interpolation order to 0, so our plot looks, partially flat in between the timestamps. And here, in this output, we just get nothing, because we don't know what the value of A is. It's just a symbol. So it doesn't know what to give us as a preview of this behavior. Okay. Event series, it's much faster and cleaner case. Basically, we assume that we are having discrete time observations and nothing happens in between the timestamps. And this cannot be reset. So, like if you want to have, for example, the node observations of, number of deaths, that's really not what we would like to interpolate between the timestamps. So, morbid example, but so if you ask for the value in between the timestamps, it's missing. And that's all what we can do. Now, temporal data, it's a more general structure. And in a way, it behaves similarly to time series and can be thought as a generalization of that, or time series is a special case of temporal data. And we assume, again, the continuous time observations, but in this case, we allow more than one path. So we can have multiple paths, but we need to have a consistent dimensionality through the paths. And this is for the slice distribution. I will show an example for that in a moment. By default, we have interpolation between timestamps. Again, this method can be set. And here, by default, this is the 0 order of interpolation, so the value is called from the left. So example of some temporal data. This is a 2-path temporal data. One path has 4 observations, the other has 3. We can create temporal data from existing time series, basically just wrap time series temporal data around the list of time series. And we just created a new object, and each time series becomes a new path, a single path in the temporal data. And now the difference between the time series temporal data is that for the value, it's not necessarily just in between the timestamp, but any value at a given time, it's going to give us a data distribution, because this is a design to study the slice distribution. So we assume really that we have maybe lots of paths, and we would like to know what are the properties of the slice distribution. An example application is where this temporal data objects actually first came to be is with the simulation of random processes. So what I have here is a simulation of a Wiener process. It's from 0 to 1 in steps of 100, and I simulate 1,000 paths. And this is the storage for such simulations of temporal data. And at the point 3, I'm going to have a data distribution. And we can, for example, plot the CDF of this distribution. We can also sample from this data distribution. So this is the slice. And this is the slice distribution that's theoretical slice. And we can compare the histogram with the PDF of the theoretical distribution, slice distribution. Okay. So the last part of the introduction is a little bit on the technicalities of it, but we have, for time series and temporal data event series, we have options and we have properties. Okay. So options can be retrieved by just asking options on the time series, and you see that most of these options refer to the dates, so there will be mostly calendar options. To find the properties of a time series, we really need to define first a valid time series object, and then just ask for properties. And so we have 14 properties that refer to times, paths, and values. Options for the event series are very similar to those of the time series. However, there's one option missing in the event series, which is the resampling method, because we don't have the resampling set for event series, as I said. Properties, also almost the same as for the time series. The only thing that it's missing is the path function, because we don't have the resampling method, so we cannot really define the path function. We don't know what happens in between the timestamps. Now, for the temporal data, options are identical to those of time series. And then when you look at the properties, we have many more, 27, because we have multi-path properties. So it's not that I'm going to ask just for the path, but I may ask for all the paths, just not for the just first path times. I may ask for the times for all the possible paths that are stored in the temporal data. Okay, so moving past the introduction, we're going to work with the weather again. I mean, for those who went to my talk yesterday, this is the commented code is the call exactly how to obtain this time series. I just have it as a shortcut here that this time series are already defined. So what we have here is the temperature. So KCMI is basically a weather station here in Champagne. So this is for the September. And say that we want to find the maximal temperature for this period. So with the direct, our arithmetic and direct function application, we can just apply maximum to the time series and get the result, okay? And what we can see from this that our original time series contains some missing information. So the weather station would say that yes, that would be a timestamp that I would record some, data, temperature data, but there was no record for that time. So I have a missing, information. So we can fix those because we have an option which is missing data method, and we can say, okay, let's fill them, with interpolation. And when you look at the plot, you see that they are small holes. I don't know if this is visible here, but you see that there are some small missing things, right? Some little pieces. So it makes sense to maybe use the interpolation, linear interpolation to fill them in, and maybe it's not going to change much in a big scope of things. So one possibility is to run the, interpolating function. Okay, we got something, and we have an error message. Okay, but in the fact, don't be afraid of this, because this message basically says that extrapolation was used. And it basically means that one of the edge values was the missing value. So what happened is that either the first or the last value probably was missing, and interpolation had to go outside of the domain and use that. And also the input value that you see here, which is 3.8, 3.68, and so on, this is absolute time, because underneath we're going to use the absolute time. I mean, for the time being, we are using the absolute time to deal with the timestamps. So when I check, this is TS1 is the first, the original time series, that indeed see that the first value was the missing value. Okay, but now when I apply the maximum to the kind of fixed time series, so TS2, I got the number, so the clean cut number. Okay, but this is still not really, I'm not really happy with this. I would like to know what units it is. Because if I look at the 32.8, and you tell me the temperature is 32.8, I go like, but you mean Celsius or Fahrenheit? Because that changes the picture completely. So we know from the weather data that I used that the temperature output is in Celsius. So what we can do here is to wrap the values from the time series into the quantity array, add the degrees Celsius, and then use the dates from the time series to create a new one. And then, Thank you. I don't know how the Polish spells, and in English it's just completely off. So yes, thank you. But anyway, we got nicely the 32.8 Celsius. So we had a nice warm September. For those people who do not operate in Celsius or are really prone to typos in this, like me, we can actually convert to Fahrenheit. So what I'm applying directly here is just a unit convert on the whole time series to degrees Fahrenheit, and then I can plot this, and so now the plot is filled. It has the label of the degrees, and then we can, if you want, we can find the maximal temperature in the degrees of Fahrenheit. So, okay. Second example for this type of manipulation is I have a financial time series in US dollars, and again in the comments is the way to get this data. This is a Starbucks stock prices that I wrapped already in the quantities. So we have dollars. So now what I would like to do is to know maybe how much this is in euro. If I apply unit convert to euro, what it's going to do, it's going to pull the current, conversion rate. So fine, or not fine. Yeah, but I am on the cable, so it should be fine. So let's hope that it's going to, fetches the current conversion rate eventually. Okay, so assuming this works, we'll see. Yeah.
Are you using the current conversion rate, or do you use the conversion rate of that particular case?
No, so my point is that if I use unit convert directly, like you see here, unit convert, TS, time series, and euro, what it's gonna do, it's gonna try to connect to the server, pull the current at this moment, as whatever the information we have on the server, conversion rate, and then apply it to the whole time series. And well, it is somewhat useful if you have, for example, a current value and you want to convert that. But what I would like to point out that I think that important for this type of analysis is to actually pull the historical conversion rate. So this is again commented out called how you can get the time series that I have for the rates. This is through Wolfram alpha call. And you can define the rates, and you can see that my rates are the euros per US dollar. And then what I can do is to directly multiply the rates times my original prices to get the conversion. Okay, and I cannot plot everything, but I can plot this. So I'll ignore the plot legends again because it's not. So that was maybe better to comment this out. So this is gonna be directly multiplying to time series, and then you can also see that our timestamps resolved to the right way. So I have one more example here about the direct arithmetic of the time series, and it's a very simple example of addition because I would like to just mention how the timestamps are being resolved when we have misaligned time series. So here I have two time series, and then I do the number line plot. You kind of see where the timestamps for each of the time series happen. And you see that some of them are in common, some of them are not. And then if I define the sum, so I can just add TS1 plus TS2, you can see on the plot that I have the sum. It's kind of the duration of the sum time series. It's in between the durations of all both time series. And so basically what happens is that we first find the common duration of the time series, and in this case it's this interval between 1 and 3.5. And then we look into this duration and find the union of the timestamps. And then on this union of the timestamps, we're gonna do the addition because we can interpolate. And so this trick works only when we have both time series. It's not gonna work the same way for event series because we cannot interpolate in between the existing timestamps. So that's gonna be the times. Okay, a little bit on the processing functions. So we have the whole list of functions which kind of start with time series and something, and they are specifically designed to work with the time series. I will have example here for time series window because it does do it is something with weather. And I like to work with weather. But basically, we had a Hurricane Matthew that passed through, Caribbean 3 weeks ago. And I looked up NOAA buoy on the Caribbean Sea. And this buoy registers the certain things like temperature or winds and so on. So you can actually go to the website of NOAA and you can extract this data. And what I did was to get the text file and then do some processing. I could, after the talk, explain if anybody is interested. And created a time series. And this is for 45 days. And so when I plot this, it has kind of two components. It's the sustained winds and gusts. And when I look at this, it kind of looks meh. Okay, and I know when the hurricane happened. So what I can do is to kind of narrow myself, zoom into the window of time when it actually happened. So I'm gonna start at the 29th of September. Automatic goes to the end of the time series, and then when I look at this, I kind of see the interesting thing that happened. Basically, the eye went over the buoy. Okay, so you see the speed went up, then the speed went down, so we have the I, and I see something interesting going on. Convert to the miles per hour. And also, instead of converting the whole time series, we have a useful thing in visualizations that you can just set the target units in the visualization function and then just plot the time series with the new units in the visualization. Okay. One remark on the time series map: even though we have a direct, function application on the time series, that doesn't make the time series map being obsolete, because when we in this situation we have a three-dimensional path here, and if I apply just maximum directly to my time series, then I just got the one single number, which is maximum of all the components. But if I would like to find the max for each value, then I would exactly go with the time series map. So this function is still, useful especially for the vector value time series. And this is the list of remaining other, processing functions that I will not talk about. I'm going to talk about the moving map. So moving map can be used to do the smoothing and thinning. So I have, again, this is the same data, the window data for the Hurricane Matthew winds. As you recall, I had 2 dimensions for the sustained wind and the gusts. I would like to just work with one of them. So I'm going to take the first path component, and it's going to be just the sustained winds here. So 12 hours moving mean. That means using the moving map with mean on the wind, which is my time series, and then specify the 12-hour window. And by default, that the windows are placed on the right. So the plot shows us exactly how this looks like after smoothing. But I would like to also thin my time series. So in this way, to thin this, I'm going to specify that the placement of my windows happens every 6 hours. So I'm still 12-hour windows, but I'm going to place them only every 6 hours. And when you compare now the path lengths for each of the time series, original, smoothed, and thins, you see that we change dramatically when we placed windows every 6 hours versus the previous result. However, you see there is little difference in the plot between the smoothing and the thinning. So we're going to save ourselves, if we have control over the windows, how many windows we would really want to place. And the new thing also is that we can now specify the positions of the windows with more precision. So say I would like to specify them every 6 hours, but I want to start at midnight. So this is my position spec. And here I have two moving maps because I would like to place my windows on the left or on the right, just to kind of show, illustrate that. And then comparing the first dates, you see that we start at different times. And the first date is the actual first observation in the time series. The second is the simple, moving map application when we just had the thinning every 6 hours. But then the third and the fourth one, they will have on the full hour, because we wanted to start at midnight, so then we go every 6 hours from midnight. So that's going to be here always on the full hour. And here's just a timeline of the stubs, so you can see how they are aligning depending of our specification of the windows. Okay, time series everywhere. I just want to show that we have time series happening throughout the Wolfram language. I'm sure I'm not gonna get all the examples around, but some of them. So one of these places where we can encounter time series is a data bin. So I have a data bin defined. It should be empty. It is. I can send some counts that I call observations to the data bin. You can see that they are actually, the counter is going on the data bin icon. So I went to 20. Then if I apply time series to the bin, it's gonna return all the possible time series that I have in this data bin, but I can extract the exact time series that I want, which is called observations. And we can plot the observations. I don't know what happened. Started again. A break in the network. Okay, and then I'm just gonna clean the bin. I'm running out of time, but I would like to mention that there is also audio properties. So when we have the example of some audio, the local measurements for audio will often return to time series. We get some sampling and we'll return the time series. And we can easily then just get the summaries on the time series. What I find interesting is to generate the time series. And since I cannot really get the sound out of here, sorry, for some reason, this is uploadable from the Puffables. So maybe just for later if you want to download. And the other example is the Wolfram knowledge base. So we get this through the entity. Lots of entities now will give us the time series. So this is the distance from Earth to Sun. So we got the time series. Right now we can get the distance. Right now we can convert this to the astronomical unit. We can plot our time series. We can find the mean and the standard deviation of the distance. This is another example of the direct arithmetic for the time series. Find the force of attraction that the sun exerts on the Earth. It returns again the time series because the distance was time series. And then we can convert the mean of this force into the newtons. And one more thing here is that when we have, for example, population of the country, and we have dated population, it's going to give us a time series. We can extract the first value, for example. We can plot. You can see that the population is kind of going, not going. What I have here is just a linear model fit to the log of values, and also using the find fit by the sigmoid function, just to kind of see what happens. And we see that the population is tapering, out. And so since I'm close to the time and it's close to the talk, I want to thank you. And I wanted to advertise the related talks, but I think unless you have a time machine, you won't be able to actually attend because they already happened. But I think that for some, the notebooks are available, and for other, you might talk to the speaker. So if there are any questions, then